If anything, we should be looking for technologies that allow us to reduce latency. Oh, I'm not supposed to be talking. I'm supposed to say, hello everyone, welcome to Handmade Heroes, where we code a complete game live on stream. Sorry, I was in the middle of saying something about the fact that I don't like game streaming. Welcome to Handmade Hero. Today we're going to be working on some lighting stuff. If you haven't seen already, our comic Kickstarter, it's in our last week right now, and it succeeded. That means if you're interested in checking out our comic, you will be able to get one if you back our Kickstarter. It's the banners on our Handmade Hero page, so it should be really easy to find. I think it's at the bottom of the Twitch thing too. I'm not sure though, because I never really know how to get the Twitch thing set up properly. Today on Handmade Hero, I sort of had a thing that I thought of this week, as often is the case when, we're spending a week waiting for the next Handmade Hero. My brain is still kind of thinking about things in the background. And one of the things that I realized, so a couple things. First of all, we were looking at some code for, if you take a look at what's going on in Handmade Hero right now, there's a couple of things that we're wanting to do. One is we just want to speed up the lighting calculation so that we hit 60 frames a second pretty reliably. The other one is reduce some of the flicker. I think I have a good idea of how to reduce the flicker. I may want some procedural flicker in there anyway, but I'd rather have it come from me adding the flicker than from the fact that we can't do very stable lighting because we don't have enough ray tracing power behind us. But what I would like to do is talk a little bit about the spatial partition stuff, because I thought of something and I wanted to measure some statistics today because I realized there's some things that I'm probably doing dumb that we might be able to do better given the nature of the architecture of the game. So, if we look at our lighting code, and we wrote this HH Lightprof system to profile what we're doing with the lighting, and we actually have a way to use like our old KD tree model, which actually isn't quite a KD tree. It's actually like an AAB tree that just doesn't happen to use that feature much. It's sort of like a binary AAB tree is more what it is. That happens to always use split planes that are aligned to axes, which is not really a KD tree. And one of the interesting things that we found when we put this in, and it could just be bugs, so, we don't really know yet because we haven't done a lot of work to really determine what exactly is going on in our system to verify correctness. What we can see is our old, running the stress test on our old KD AAB KD tree, however you want to say that, AAKD tree, is 6.27 seconds the stress test is. If we switch to the newer KD tree model, which has a much abbreviated walk pattern, but when you run it, it's way, way slower. And this is really interesting. But there's a couple things that I think make that a rather obvious thing to have happen in some sense. And we should probably go over them, but I also realized one other thing that I hadn't really been thinking about and probably need to think about, which is that we may not want this kind of tree at all, and it may just be overcomplicated for our needs. KD trees are very popular in ray tracing. They're very popular in ray tracing because I think they have the minimum amount of checking you need per level of the tree to descend down to the bottom of the tree. And so at some level, it's like, well, it makes sense to use a KD tree because we know they're going to be good for ray tracing probably. But for our particular geometry, I also don't know if they're the correct attack plan, and I wanted to talk about that. Now, what I would like to do is I would like to profile our own. You can see how long this is taking, so I don't need to finish running this. My point is just the KD tree thing we dropped in there was actually quite bad. But that may be because it's buggy. We need to do some debugging on it, which we might want to do just to verify. But what I did want to do is in the old KD tree case, so this case here, which runs in 6.7 seconds or whatever, the stress test case, where we just run it over and over to see what it ends up getting, we end up with that timing, and we collected some statistics, which is the total number of tests we perform, I believe is what that is. The partition tests, which are tests that don't tell us a collision, they just tell us, like, go down this part of the tree or don't, right? And then we say how many leaf boxes we've tested. So when we're running this, we know that throughout this test, we test, and I believe this is divided by the repetition count. So this is actually not the total number of tests performed. It's the amount in one run. So this is what we do like on a frame in the game. So we test, for every leaf we test 4.7 partitions, right? And in here, we also know that we test a total of 500,000 roughly leaves, and we test a total of 2.3 million partitions, right? And what I was curious about is per ray, because we don't print out the number of raycasts here. I was curious to know what the average number of partitions per ray is. Does that make sense? So if I go into the code here and I ask it to count the number of rays, I'm not sure if it may already. I think we were counting that already potentially, so it may be that that's already here. You can see like total casts initiated is there. So I want to say that really all we need to do is actually use the data we're collecting there that previously I wasn't interested in, but I am sort of interested in it now. So when we come through here and we print these out, I'm going to print out another line here, which is just how many partitions per ray we actually were testing, and then also I guess maybe leaves per ray, so that we can just find out like for every ray we cast, like how many is that, right? Like how many is that actually happening? So in here we've got the total number of leaves tested and the total number of partitions tested, and I should now be able to do like total ray count, or total rays initiated or whatever, right? In here, like so. And looking at that, so what's interesting about that, though, I'm a little confused. When I'm looking at this, total partitions tested is actually a summation. Oh, it's zeroed every time. So that's good. I was like, I don't divide by the number of tests. That's okay. It's cleared every time. So this is just the ones from the last test, which is totally what we want. Like, we just want one test worth, because it's the same on every test, because configuration's identical, I believe. I mean, maybe I don't know if the series number is reset every time, so it might not be quite identical every time, but it's like close, right? So anyway, if we take a look here and we look at like total leaves tested, total partitions tested, and total rays initiated, if I just count the total, well, here's the total cast initiated. It's right there, actually. So I actually already have it. Total cast initiated. And I just look at total cast initiated like so. I should now be able to print out, in addition to the existing data, information about how many of these things we're testing per ray, because that will give me some idea of like whether or not this is the correct model, because I don't actually know what those numbers are. I think we looked at them a long time ago, but we're not, but I don't remember, right? So this is good information for me. So in our fast version that's actually doing AAB testing, right? So it's actually testing a full AAB. It's not even doing a KD tree test. So it's doing better than a KD tree test because it has full bounding information on these things. For this kind of geometry, which is a lot of little cubes, like roughly, I mean, they're not actually cubes. They're, rectangular prisms, you might say. But, they're stretchy cubes. We're testing 5 partitions per array, and on average, and we're testing 24 leaves per array. Now, here's the thing. Because our geometry is very grid-like, I'm wondering why we're not just using the lighting voxel as a voxel containment field, like basically like a thing that says, here's where all, like each voxel node just has a list of the boxes that are in it. And the reason that I say that is because if we were to do that, then we would, in theory, just be able to walk the voxel directly with a known pattern that had no branches at all. Like, the only branch would be in the leaf branch that we already have. Like, how many leaves were in this branch, right? So if you think about what's going on there, I mean, there's some things about that are very attractive too. Like, if you have a known pattern for array, we could test box-wise instead of ray-wise too. So we wouldn't have to test ray bundles anymore, which means we wouldn't bifurcate ray paths either. And so I'm just really curious if maybe the idea of using a tree is just inherently flawed and we shouldn't be doing it, right? Because if we just used a voxel and walked the voxel, we would already know exactly the pattern to walk. And furthermore, we would know the pattern for every voxel. So, like, the branching would be very limited. The only two branches you would have would be the loop that loops over the voxels to test and the loop that loops over the leaves. So you'd have two loops and no conditionals at all, right? Oh, leaves in plain switch. Someone was mentioning in the chat that I accidentally switched that. Thank you. There we go. Wow. So that's actually even more convincing for what I was just saying. Wowzer. So 24 partitions per ray, that's like way too many, right? So I think I may just say, forget it. I know we spent a lot of time looking at how to walk the tree, but sometimes you spend a lot of time and then realize what you're doing is stupid. I mean, that's the nature of optimization work. I'm not sure we even want to go down this route. So let me explain what I'm talking about here. This is what I was thinking about. Let me just explain it to you visually so that you understand, so that you're in the same headspace that I am, or at least you understand my headspace. So if we jump in here to, I don't know what day this is, day 598. So essentially what I'm talking about is grid raycasting, right? And what I was saying, let's just do it in 2D because it's the same in 3D. There's not going to be any difference. It's just a little more expensive because there's more cells. But let's suppose that you were just doing this in 2D, right? So currently what we're saying is, look, we got a voxel, and we're going to start somewhere in the voxel, and we're going to do a raycast, and we're going to bundle 4 rays at a time, right? So we're doing 4 rays at a time, and we hope that they kind of go out in a relatively similar direction. And we know they sort of do because they're in line with the octahedral map. So they're sort of close, but not that close. And if you look at how they actually progress out into the world, what we were doing before is saying, well, all right, so there's all these like cubes around, right? And we're trying to raycast against the cubes. And so what we're going to do is we're going to split those up into like bounding series, right, that split things apart. And we're going to test against these like bounding volumes that result in those. And we're going to like traverse down into them to find which leaves we should actually test against, right? So what that ended up being is like we would have an AABB and it would have 2 sub AABBs underneath it like so, right? And that would have 2 sub AABs underneath that, and so on. And then eventually we'd have some lists of leaves down at the bottom, right? And they're not really lists, they're actually just in an array, so there'd just be a count. And then we'd test against those, and that's how we would produce our raycast, right? Now, the problem there is that every single one of these tests is fairly unpredictable and random. We don't know whether we're going down the left side, the right side, or both. So we can't really predict and preload this. The processor is just kind of sitting there stuttering, wondering which side is going to go down, and it just has to deal with that, right? Furthermore, if we have one ray that only would need to go down this side and another ray that would only need to go down this side, that wouldn't actually work either, right? So that's the problem that we currently have. And I don't know to what extent I can do this, but I was wondering what would happen if we just, for example, instead of doing that, just cast one ray and used the loader, like we actually took and loaded in serially all of the leaves that would need to be tested by using a grid walk. So instead of the tree, we just say no. What we're going to do instead is say, we know that we're going to be casting on, we know that we're going to be casting on this thing. And if we were to cast a single ray, we know that that ray would have a predefined pattern in our grid, or voxel as the case may be. So we know that, for example, you would test the one you're in, the one below it, the one next to that, the one below it, the one next to that, the one below it, the one below it, the one next to that, right? This pattern is deterministic. We are always casting from the center, and we know all of the rays because they're in our sphere, like our sphere cast database, right? We have that, and we're always pulling from a distribution that we already know. So we already know the walk pattern, right? The walk pattern is known. So we can just store a list of voxel indices relative to the current index, and we know what they are. Right? So that basically means that we can start by assembling a leaf list, and then we can literally just load the leaf list, right? So we actually can do this in two loops. One is a while loop over these, right? To gather all of the indices that we need. And then another is a while loop over those indices to check them. But that's it. So there's no descending, there's no nested loops. We can literally just do it in two passes exactly. And there's no branches and no ifs because there's nothing to test. It's completely deterministic. They'll walk every time. The only thing you're testing is when you got to the end. So when I got to the end of this and when I got to the end of that, those are the only two tests in the entire thing. Now, I don't know whether it's cheaper to copy the whole thing or just copy the index, but that's... I really don't know. That's a tough call, and I really have no idea what the answer is. We'll probably have to test both of those and see which one is faster, because I have no idea whether it would be faster to have our grid squares store the occupants of the grid square and as indices, or if it would be cheaper to store them as copies and then copy them in. Furthermore, there's a deduplication in a sense, in that you can also, if you want to, try to deduplicate leaves rather than test against them twice. And what I mean by that is, like, suppose there's something here and you would have walked all three of these as you like raycasted through it. You only need to test that thing once, and I'm not sure what you do about that, because one way is to just test it 3 times. There's no cost to doing so in terms of the complexity of the algorithm. It's just you're wasting time testing it the second and third times because the hit can't be any closer than you would have already found when you tested it the first time. But if you wanted to deduplicate those, you would need some scheme for deduplicating them that would involve a secondary like bit field. And I don't know whether like that deduplication then adds an if. You know what I'm saying? So it's unclear whether you want to do any of these things. Like maybe you do, maybe you don't, but I really don't know. So those would be specifics of the algorithm that we'd have to test out. But because that's so clean, I feel like I at least want to do one thing before we spend any more time on tree walks, which is to just say, if I was to take the current geometry and dump it into a voxel, what would the general occupancy of that voxel end up being? So let's suppose we took the actual light lookup voxel and we said, let's figure out anywhere that a geometry element that we're testing, an occluder, right, or a light source. Let's find out where any of those would have entered into the voxel, and we'll just print out like the max occupancy of any voxel at that point, right? And then we can get some idea about whether this would be efficient or not. And then I can maybe we'll just do it. Like maybe this is what we'll do because maybe this is a lot smarter. And we can sketch out the routine and just see today if we think it would be. It requires casting one ray at a time. So that part may be bad, right? You don't have to, but it would make things way slower if you didn't, I would think, because you'd rather not test a bunch of things you don't have to test, I would think. I mean, I don't know. So anyway, just a thought. And so if you were to do that, then there are some nice side effects, which is that you don't have to decouple rays to compute the hit afterwards because you only have one ray. So you're actually computing on the faster side of things, potentially. And presumably that's a good thing. Like, so presumably when you got into, it's just one CMOV and not a bunch of selects at that point. So it's possible that this routine gets faster in the lighting act code. It's possible that in the raycast code, like this stuff could get a lot faster because rather than doing all these selects, you're just storing one variable, which is who the best T-ray hit was, who the best index was, rather. That you could then, look up at the end or something. So I feel like maybe it's got some promise. I don't know. Hard to say. And so when you do these, you would do exactly the same thing that you do here, except you would collapse on T-ray. So you would have to do a min on T-ray each time at the end of this, is what you would end up actually doing. And so again, like, I don't know if maybe that's not as good because when you do the min on T-ray, you'd have to know which one you did. I guess what I'm saying is there's a MOV mask in here that wasn't in here before, right? And so that's a thing maybe is bad, right? And again, this code is so touchy that I'm not sure I can make a strong prediction about it either way. So again, I think it would just be something we'd have to test out. So if we imagined like what this raycast routine would look like if I was to do it the other way around, right? So imagine we took this thing and said, look, we're just gonna like change this up a little bit. So instead of that raycast routine, there's going to be like a different one. Doesn't use the stack. It doesn't use that stuff, right? So in here, we would just say, okay, there's going to be a thing that's like grid raycast or something, and it takes the ray origin and the ray D unduplicated. So you're just calling like one cast each time, right? And when we go through here and we get out the this information, we would be doing the same thing here. This total cast initiated looks like it's a little low. So those numbers are a little false because we're actually casting 4 rays at a time. So that should have been, so these numbers are not as bad as they seemed. They should be divided by 4. So it's more like 6 partitions per ray, right? And like less than 1 leaf per ray, right? I mean, sort of, because it's times 4. So that's actually not that bad, right? It's not as bad as I thought it was going to be. So we'll see. So maybe this isn't as good. Maybe this won't be as good as I did them, because if you look at that, it's only doing it once per raycast, right? Which is not as good. So really, you want in terms of total rays, like we would want that to be times 4. In fact, I could do that. I'm not sure how we would want that because these are sort of different. So maybe the right way to do it is to say, look, this is like 4 and this is, 1, And we could change that to be called total rays initiated as well, total rays cast, just to make it clear what was happening there. So anyway, inside something like this, when we come through it, I'm going to get rid of the debugging for now because this debugging would have to be different. So we're going to save that for a little bit later. And I'm also going to get rid of the branch here because we're going to write a completely new one. So this can all go away like so. And yeah. So when we look at what would happen here, there would be 2 phases of this. So one would be a phase where we loop through all of the, all of the stuff in the... One is we loop through basically an array that tells us what to cast. So we would do something like this. This is like our walk index or something. And we would have an array. So in here, there would be a thing that's like which grid square to load, if that makes sense. So in here, we would have a a load index pointer, you know what I'm saying? And it would be like our walk table. We would get that out. In here, we would basically say like, and we could even write this a little bit more cleanly where we just say like do, while walk count, and so on. So each time through here, we'd say like, okay, at the end, do a sub and a step out. In here, we would load off of the load index. So we'd do like a load index ++, and this would be what we'd actually be loading here, right? So each time through here, it would give us some index to load. And so this is like the leaf index that we would get. And we would just copy that leaf index into our testing stack. Now, we can either copy the index or the actual data. I'm going to go with data for now because why not? So when we load this in, we would just like place it into the L1 cache in the right location, right? Like roughly, probably using the right buffers. So we'd probably just like stamp it out in an XXXX, YYYY, ZZZZ pattern, right? So in here, what we would want is something roughly like this, where we say, okay, we're going to have like box information here. So we're going to have like, box mins, box maxes, right? And I don't know what the size of these is going to be exactly, but something like this. We'll clean this up as we go. And then we would also need probably the ref colors. I don't know. I mean, like I said, we could also just have indexes that we're flattening out here. So we could just do the index array and then load 4 at a time later, but I don't know. It's, again, hard to say. So then we've got like ref colors and emissions, right? So I don't know, it would be something like that. I don't love this. I feel like the way that we do emissions is not very clean. Feels like you shouldn't need to do what we're doing. So if you look here, you can see what happens. It does this nonsense where it says like, all right, like take the probe sample normal in the emission direction, right? And do some nonsense with it and then like combine those two. It feels like we should be able to send back something better than that. But I don't know. We should look at that later. Anyway, we know we need to send these back, and I think we need the normal too. So it would be something like this. Right? So these are the things that we would have to load, and we would load, them 4 at a time. And that looks, a bit large, but again, like in terms of how many realistically there are going to be, there's probably not going to be very many of these that we actually touch. So assuming you touch like maybe 16 of them or something, if you're talking about 16 times 3 times 4, that's 192. So, at some level, keeping even 8 of those is minuscule, right? So reading and writing these is basically just going to be like one cycle anyway, for the most part. You know what I'm saying? It's just not probably a huge deal. So doing the gather here is not awful, I don't think. I don't think, right? Famous last words. So yeah, so when we look at writing these out, basically, like, I don't know what the most efficient transfer method's going to be here, but, you know, in terms of, like, getting these boxes, it's solution, right, like, box, what is it called? There's some name for this stuff, boxes. It's solution boxes, leaf index is what we're loading here. So we're loading in one of these lighting boxes, and this is our leaf. Excuse me. And what I want to do is I want to take the leaf data, so everything that was in the lighting box itself. I want to take the leaf data, and I just want to, like, unpack this stuff into SIMD format, right? And I want to pack it for this specific processor that comes after me. So in this case, what I want to do is say, all right, like, if we take and we load out of the leaf, the boxmin, the boxmax, the refc, and the pack dot is light value, and leaf container can go, that's not a thing anymore, so we'll deal with that later, but so we're gonna do something like that. And so if we wanted to then start packing these, what I want to do is say, okay, the boxmin, like, each of these things is we're going to be writing to sort of sequentially, which means I may want to do this slightly differently. I may want to say, like, walk index equals 0, walk index less than walk count. Writing this routine well is going to require some thinking about what the assembly looks like. So again, I'm not going to think too hard about it now. I just want something not totally terrible. So we'll see. But again, like, I want to do this correctly, just in terms of theoretically, and then we'll think about how to, like, structure the walk, ideally at some point later in the future. Okay, so I want to do boxmin, walk index, and as the walk index goes up, I'm just going to be, like, addressing these, like, sequentially. So actually, like, looking at it this way, it's going to be more like this. Right, we're going to be writing to these as F32s. So we're storing out to memory and then we're loading them up wide, if that makes sense. So I'm going to look at this boxmin as if it's F32s. I'm going to assign to them sequentially each individual, like, boxmin part, right? So what I want to do is I want to say, let's look at this as if it's an F32. As if it's an, well, I guess actually I don't even quite need to do that. I can actually use the dot syntax here. So I want to assign the, every 4, I want to move on to the next one. And I want to address the, like, you know, formatted element of it, right? So again, all I'm doing is just I'm swizzling these into a SIMD, you know, friendly format. That's all I'm doing here. So, you know, I'm going to take whatever the X component is, and I'm going to stick it into one of these, like so, right? And I want to do that for each of these. So we could also do, like, maybe this is our, you know, primary index and our secondary index, something like that, or our lane index. So primary index is walk index over 4, walk index mod 4. So I've got our primary index here and our walk index here, like so. And then I just want to assign each of these. So I'm unswizzling these into place, right? And we're probably going to want to do these with actual SIMD ops, right? So like I said, The problem with that is we're going to have to do like 4 wide loads. So we have to like queue up 4 indices, load 4, and go forwards, which is harder. So we're not going to start with that, but we may have to get to that when we actually try to optimize this for real. But we'll see. So if we're talking about that, then we'd need to like load these up. So we've got box max here. And this actually, I guess, isn't the case because that's determinable later. So never mind with that. It's only ref color that we'd actually need to store there, and emission. Right? So yeah. And these could be stored much more compactly. These could be stored as a single packed value. So like the emission value, like an RGBA, so like these... Like at some point this crap has to get worked through. And we can do a lot better job compacting down the light information to some encoding that's not so unwieldy as this particular thing is, but that's sort of a separate discussion. We don't have to care about that at the moment. Also, this isn't hit ref color, it's just ref color and emission. So here's our ref color, like so. That's called ref C. And then finally down here, we would just have that, like, emission. And the emission, yeah, is, again, is this would be .x.e, actually. This is the wrong way around, right? It's that way. Oops. Accidentally deleted the equals. So this is more like that. And that should give us what we need. And for the emission, that's just going to be the standard, because that's just an F32 4X. So that's just going to be the standard, where we just say, look, whatever this thing is, we either provide a 1 or a 0, I think is how this was working at the moment. So it's like if it's a light, it's 1. Otherwise, it's 0 is all that we actually do. So this loop would be all we actually need to do. And this part here could be loaded up better, like I say. So this doesn't need to be an if. And at the moment, it really probably won't even be an if. It might actually just be done with a CMOV or something. But this doesn't have to happen, because in the future, I think we can pack these better. This should just be packed like a 8-bit RGB emission value or something like that. Is what we should have. Something like this. I mean, that's my thinking anyway. We'll see. So once we unpack everything into these, then all we would do is do our actual test by counting how many of those we had. So when we do our loading, well, this is actually this is not true. So we would have a separate walk here, right? Which is the while that loops over, like, this is not quite right. So that's a lie. This walk index would tell us the leaf indices come out of nodes. So there are 2 layers here, right? For each of the things, we do have an unpredictable branch. Like I said, there's the one here, which is just, it's a known number that you loop through. So that one's a fairly predictable branch. It only misses the last time. But this one is the unpredictable branch. Like I said, there's 2. There's that one, and then there's the one that's here, which is we don't know how many of these there are going to be. Although that's not really that unpredictable. Never mind. Okay. So in here, this is what we actually need to do for... Wait a minute. Let me just make sure we've got this right. This is not necessary, so that wouldn't be the case. And so it's just this one here is the only thing we actually need to do. So we would be doing this, and that all goes away. like so. And then this part here is still the same, I think. Well, actually, it doesn't have to be. This part can now be done in scalar or done outside by assembling multiple hits, right? So yeah. And we could preserve the structure of the routine if we want to by just looping over each ray. So we could do this, but it seems better to just call it 4 times and get the results back. And like I said, since you want this to sort of be done as part of that ending code, I'm not sure how we want to deal with that. Like, this kind of has to now move into the external code. Do you know what I'm saying? Like, this part here now has to move into the code that actually calls the raycaster. Or you can have it be 2-stage, but it's something like that, right? So, you know, as those come out, you then load them up as 4 things. So again, I'm not sure what we want to do about that, but like this part here, right, just becomes a little crunkier because, yeah, you have to deal with that part. So I'm not sure what we want to do about that. I'm going to leave that temporarily and just think about these for the moment. So assuming, again, that we're only doing one, this right here is like the leaf loop. So this is just going to be like looping over the leaf indices of a particular node. So it's like this. We pull one out, we pull out whatever the grid node is that we're talking about here, and that grid node, so this is our lighting grid node. This is all it is 2 things. It's how many of these there are, and an offset into the list, right? And again, I don't know if these should be indirected or not. Maybe they should, maybe they shouldn't. I have absolutely no idea. So let's assume that they are indirected for now. Like I said, so this would be, you know, start index 1 past last index, and then we loop. And this is telling us like what in that array those are going to be. So then our leaf index is like solution spatial leaf indices, and it's just this, right? So we grab one of those out. We now have our leaf index. We look it up and we copy out, right? And so again, like I said, the thing I don't know is should those just be flattened? And I have absolutely no idea whether they should be flattened or not. Maybe, maybe not. Totally don't know. Have no idea. Furthermore, it may be that not only they should be flattened, but they should actually also be like swizzled so that you load 4 at a time and then you... Right? But I mean, then what would you do for nodes that don't have 4 things? It wouldn't work, like, because you are wasting raycast at that point. So unless you had an average of 4 things per node, which I don't think you will. I mean, maybe, but that doesn't seem like a good idea. I don't know. So that's a little temperamental. I'm not sure what we would want to do there. If you ended up having an average of 4 things per node, typically, like either 0, 4, or 8, were not uncommon like discretizations, then that might not be bad because then you could just like swizzle them once at the beginning and not have to swizzle them here. So I don't actually know about that part either. I'll put that up here. And one of the interesting things about that, so now that I'm thinking about that, maybe the answer is that's just what you do. Because if you load 4 boxes at a time from the walk and that's just what you do, you don't need the second loop because there's no need to save them now, right? To heck with it. I'm just going to say that's what we do. So if we make that concession and say we're at 0, 4, or 8 boundaries, basically, then this comes into the middle now, right? And this loop is just, look, we walk over some stuff. We've pre-swizzled this crap already. So basically this happens at tree construction time. So we're still going to do this, right? Like that still happens, but it happens at tree construction time. So in like build spatial partition for lighting in here, what we would actually do is do the grid build. Right? We do the grid build here. We cross our fingers and pray we don't blow out the cache doing that. But assuming that it stays in L2, which should be 256K, which it probably will most of the time, maybe might not do that. But we do walk the grid in order, so we may get enough reuse on rays. I don't know. Doesn't matter. We're going to do it anyway. So in here we would say, okay, we go through the walk indices and the leaf indices, and we literally just load this crap out directly. So in here, when we say, look, we have a spatial grid node, and that spatial grid node is what we loaded out of the walk table, we're then going to load leaves directly out of that node from our spatial, grid leaves. So this is a direct walk rather than, in other words, this is this. Right, so we basically say, like, look, load this thing out of here, and we're gonna, like, test that crap a bunch of times now. So inside the leaf, we load up the box min and the box max directly, like so. And then when we do this stuff, and we're doing, like, the Hadamard product with the invray-d here, this invray-d is actually the thing that's duplicated, not this, right? So invray-d is like load opt up, right? So this, right, is load opt up from this ray-d here. You know what I'm saying? And so, I mean, we could have it pass us a 4x, but I don't think there's any point in doing that at the moment because it has to be loaded up either. This we can take because we know it's that way, but this is actually just a single one. So this is like, single array D instead, and then here we load it up. We do a load up, right? So at that point, yeah, invray D is the thing that actually happens. So this all stays the same, like all of this, right? This is all exactly the same. I don't know what close enough does. Nothing. So I'm not sure why that's there anymore. That would have just been getting thrown out by the optimizer anyway as useless. But so in here we would then what we would need to do is figure out what we're actually storing here as far as like our tmin, tmax stuff, right? And I think you can just do exactly the same thing, and then at the end we're just going to load out the one we actually care about, I think. Right? So in here we loop through and we just say, none of this is necessary. So we're literally just talking about the same crap as before. So like we just go into this thing and say we're keeping exactly the same crap as we were keeping before. Oops. Oh, it's already there. So we're keeping this exact crap. This exact crap is exactly what we're keeping. All of this stuff, right? Yeah, and off we go. Yep. So then when we come through here and we've done all of the selecting, like we now, at the end, the difference is that we now have like instead of having 4 different rays that all need to have an answer, we now actually have like one ray whose answer is spread across multiple values. Now, the good part about that is, like, the good thing about that is we don't have n-way loads in SSE, so we have to process these serially anyway to look up their lighting values. So that's actually a win. The thing that's not good about this is figuring out which one of these to pick is actually non-trivial, because actually getting a specific one out is hard. And it gets easier using later versions of the instruction set, but as for just sticking with SSE 1 and 2, I'm not sure what we have for extraction that doesn't involve, like, I just don't know if we have. I don't know if we have a lot of ways to do that. That's not going to help us. Yeah, so I don't know. I'm probably not explaining this because I'm thinking about it in my head and I'm not saying it, which is not helping anyone. I'm just trying to figure out what would be the quickest way for me to get the results to be to use a comparison to get what the results actually are. Because once we leave the 4 wide path, we need to know which of the 4 was the minimum, right? That's the tough part. And so needing to figure out which of the 4 was smallest is the problem that we have. And I'm not sure how we get that to happen efficiently. It's not really something I've done in SSE hardly at all. And I don't know, like, what if we went a little higher up? What if we let ourselves go up to like 4 point something, right? Is there some way that we can extract something numerically? So those are all immediates, so no. Those are all, oh, that's not an immediate, but that inserts that value, right? So that doesn't help us either. Here, let's do this. And I'll look at 3. I mean, if we have to add 3, I guess I wouldn't cry about it. But so let's look at swizzles, moves, miscellaneouses, and general support, I guess. I don't know. Just trying to figure out what I might be able to do here to get something out that wasn't based on an immediate, and there may just not be a way. Because if that's the case, then it's like a switch statement or something, right? Which is not my favorite. It's in the faster part of the routine. It only happens once, so it's not the end of the world if that's what has to happen. But it would be nice if we didn't do that. But I'm not sure if there's any way to not do that, right? Like, I'm not sure there's any way to tell it, like, hey, don't do that. Shuffle it instead or something. Yeah, I don't know. So I think what I would have to do at that point is I'd have to just do, unless I'm missing something, I have to do something with like a table or something, right? I mean, or I guess I can do a store and a load using the mov mask value. So like if I do the move mask, if I do a move mask PS, I can get the high bit, which means that if I do a comparison, I should be okay. So basically, like, if I take the min, what I want is the min, and do I not have a min? Seriously? There's a min. What are you talking about? I mean, you can definitely take the minimum of two things and it produces the result on the other end. Why am I... Oh, I had these checked still. I'm like, what are you talking about? Sorry. So I can do a max and a min. Like, I can do these to figure out, like, which of the t values is the one we're going to use, right? It's just kind of expensive. And to sketch out what I mean, like, why I'm saying that it's kind of expensive to do is I've got t-ray and there's 4 values in it. So if I do like t-ray, I would need to first swizzle it, right? Like I'd need to do something where I would say like, look, do a shuffle on t-ray where we produce like, 0, 1, 0, 1 and 2, 3, 2, 3 or something and take the minimum. And then, because I need to take the minimum, I need to make sure all the values have gotten their minimum taken. So I need to get the minimum of the 4 wide elements. You know what I'm saying? So in here I would say, all right, shuffle t-ray to give me, the 0, 1. I guess it doesn't really matter because you're wasting a lot of ops here, but I'm not sure how you would do it unless you just do bulks of these at a time, which maybe we need to do, but we'll see. So imagine you do this where you're just like, look, I want 0, 1, 0, 1, and I want 2, 3, 2, 3 out of this or something, right? And when I do these two, what I then want to do is take the minimum of those. So like this is the min 0, this is the min like 0, 2, 1, 3, right? So it's the min AB, I don't know what we'll call it. So I would need to do that first, and then once I have that minimum, I need to shuffle it one more time, like, like this, basically. And that would be... This is actually that. Because I want to take this and I want to move the 2, 3 down into the 0th position so it's lined up with the other one, right? And so then I would do the min t, right? Or t min is just or I guess that shadows it, but min ps, min ab, min cd. So then you have a t-min value, and that t-min value tells you what the lowest one was. And if you do a comp EQ at that point, you're going to get out like which of what your closest, which one was the closest, right? So you would basically do like t-min, t-min mask equals comp EQ, the t-ray with the t-min. That would give you 0s in all the lanes and 1s in the one lane that was the minimum. Now, 2 things could be the minimum. So it's a little bit tricky there, but after you do this compq, you can say, you know, the output mask that we get is going to be the mov mask of tmin mask. And at that point, we now finally have a thing that tells us which lane to extract, right? And at that point, we can, if we want to, load it. So we can F32 load stuff now. And again, it's not great, but I think that's how you would have to do it. So in order to produce the correct versions of each of these things, you would now have to use the mask. Now, to be fair, I think you can still do the rest of the computations pretty easily. So it's really just that one extraction of like, well, let's see. So what were these doing down here? Let's just take a quick look. So in terms of all this stuff where you're computing it, I feel like a lot of that stuff in Scalar, you probably don't have to do it this way. I'm guessing. That's a little bit hard to say. But again, if you look at this extraction that was happening down here, like that doesn't have to happen anymore. So like this can just occur like directly. You know what I mean? So yeah, so if we were to do this directly, I just want to see what we actually need. So the t-hit value here is just whether or not this thing was equal to F32 max, which at this point, we don't care about exactly. Here where we have to do the get component, that doesn't exist because we already know that that's the emission direction. We already have that information. So that's not particularly interesting either, right? This here is literally just that one if. So it's literally just, hey, when we get the actual tmin value out of this thing, which is the part that's a little bit tricky because we have to extract it using the thing, but, you know, oh well. Like all of these extractions, it looks like we were already doing them, right? So in a sense, they're not more expensive, they're the same. So in here we would do, I guess, the same thing, right? We would just say, look, if this is not equal to T-ray, whatever the T-ray values ends up being, like the scalar T-ray. Like so. And then in here where we do like the get component and all that stuff, we can just do this thing. We can just do these in one wide. Because although it was nice to do them two wide, this is the expensive part of the operation, and it only works with one wide. So I'm not sure we were really saving anything. I mean, you save a little bit, but most of it, not really, because you got to do this, and that's the part that actually costs you something. So I think that's probably okay. I mean, here's the hit P that you have, right? So you've got the hit P here, and it's just going to be that value. So it's just the ray origin plus the T-ray times TD, you know, that value. The sample n is the hard thing, like it's this ridiculous nonsense here. And so I think that's a lot easier to compute now because all you would really need to do is see which of these things is the higher value. Is it the X, the Y, or the Z? Right? I think that's all this is saying. So when you look at what the normal is, all you would really need to do is look at which value was highest. And that's something we could do probably a lot easier than this, would be my guess. So I'm thinking what we could probably do there is something much, much, much more straightforward. So we could probably do something like if we computed these values the same way that we're doing it here. So we do the center and the radius, and we look at what the delta value is between the center. You know, it's really the inverse radius that we need there, I guess. Or is it? So I guess, yeah, all we really need to do is do this computation, which I suppose is not that hard, right? It's just this. So we would need to compute those two values, and then we would need to use that radius to compute the inverse radius. So this code would work exactly the same way. It just wouldn't have to use. It wouldn't have to worry about the fact that there are 4 different values. So when it comes time to get down to here, you actually wouldn't probably do that. You'd probably do something like this. You'd probably say, like, if the scaled D is like less than, or so you've got, I mean, what are all the comparisons here that we were doing, right? Like here they all are. So those are all the comparisons you're doing. You're doing like x less than y, x less than z, y less than x, y less than z, z less than x, z, right? So what you'd probably do is you'd just do like, you know, normal bit mask, right? And you'd say, just put all these together, like, so you do these comparisons where you do each of the comparisons, and then you just like grab the bit mask out and load, right? So it'd be, and in fact, since you've got, you could probably do that more efficiently with a single mauve mask just by doing like putting those in like some lanes. So you could do like x, one of your vectors could be like x, x, y, y, and the bottom could be y, z, x, z. And then you'd only have the z ones, but you wouldn't even need them, right? Probably. Strictly out of curiosity, are we totally missing an absolute value here? I think we are. So I think this code is missing an absolute value, right? Because we haven't tested, like, another thing we have to do when we do our lighting quality pass, right, is we have to test all these things and make sure that we don't have bugs in the test case. And I feel like this is missing an absolute value. Because all of these comparisons are not quite right. They're only going to work if you're on the positive side or the negative side of both, right? You can't be comparing these things if you don't have them absolute valued first. So I feel like you would have to and them with that mask before. So I'm going to say like I'm going to say like we probably are going to end up vaporizing that case because I think doing this in scalar is probably the right way to go, but I don't know, right? So that's hard to say. So anyway, in here we would do a normal bit mask, and I guess we just need to know, like, look. We need to know two things. We need to know the signs of these things, and that's one move. So, like, the sign mask would just be one, you know, move mask of the, like, packed XYZ vector. And then the comparator mask, the like, or the greater mask, that's going to be like a mauve mask of a comparison between like packed XYZ. And I need to know like the comparison between like X, Y, and Z and Y, Z, and X probably. But once you know those comparisons, I don't know that you need to know whether, like, transitive property-wise, I should be able to determine from just 3 comparisons, shouldn't I? I might need one more, but, like, you know, you could imagine doing, like, this is, we pack one with, like, X, Y, Z, X, right? Or something like that. And we do, like, X, Y, Z, X and packed, like, Y, Z, X, Y or something. Right? Or YZXZ. I don't know. But you can see that us getting the extra one in there. But point being, once we get the sign and the greater than, in theory, we should then have a way to use a lookup table to generate the correct normal and it in, right? I would think. And so I think all we have to do at that point is do 2 loads, right? You just do like base normal, or you know, you do the normal and you do like normal table, and the normal table just has this mask in it, so it takes those compares and gets us the normal. And then the sign table, right, just looks up the sign mask and applies that, right? Although actually, so I think it's always the same. So we actually don't need that. We just need to know. I mean, I guess we still would want to load it this way so that we could Hadamard product them and not have to like build that up, but we might not even need to do that. All right, so we would do something like this, and that would get us our hit normal. Again, just a sketch of a routine. We would come through here, and we would see whether or not this thing needs to do its like moon color dance nonsense here. We would say, all right, like we can compute this. We know we already have that. The hit ref color is again an extraction, so I think this is like a get component based on that. This would also, I guess, be just a get component, exactly like we're doing here. This is the T-min index here. The emission value, again, same thing. And then the rest of this just does its thing, right? So then you're left with the transfer PPS that you actually wanted. I guess I don't need to initialize that because both paths do it. And then you have the actual raycast light value you asked for, right? And you just have to actually do something with it. And that's what you would return. I guess that's the only thing. And you wouldn't pass these down. Like that wouldn't happen. None of this would happen. You would just do this. Because you're now like not lined up for anything. So you might as well just give back the value and let someone else deal with it, right? So I don't know. Like, I don't know to what extent this is better or worse. But you can see why I'm thinking that this is a better routine. Because, I mean, if you just look even at the simplicity of it, it's just a lot clearer how you optimize this thing, because now you're just doing this one fast loop and that's it, right? And you only just have to make sure that that runs as fast as humanly possible. You may do a little bit too many computations in there, so that's not great, but you don't have any real like issues beyond that. The one downshift to scalar just happens when you have to pull the index here, which is annoying. And I'm not sure if there's a more efficient way to do that, right? But that'd be the entirety of the raycast at that point. So I would say that based on that, that looks worth doing to me. Because it's so much more clear how this routine runs, and there's so much less stuff happening in it. The only thing that I don't like about it is that I'm not sure how to quickly get that T-ray out of there, right? So I'm not 100% sure on that part, and I'd have to think about that. This may not be the fastest way to do that either. Basically like a horizontal compare. You don't want to do horizontal compares, right? Like they're not favorable. InSimD is bad at this. So it's an issue, right? And again, I'm not really sure what I would do to try and get rid of that. There are some ways you can, I mean, so if we allow SSE3, we do have Shuffle EPI 8, right? And Shuffle EPI 8 is extremely good at doing things quickly. So, but I'm pretty sure you can't do it if you don't allow SSE. Is that SSSE3? What is SSSSE3? Oh, it's the supplement. Sorry, it's the supplemental streaming SIMD. I don't think I ever internalized the fact that that was an SSSE3 as opposed to an SSE3. But evidently it is. There's PShuffB right there, right? Okay. So yeah, if we take a look at the shuffles, they're like, I think that's the only way we could really do something fancier there, I think. So if you imagine like using SSSE3, which I wouldn't necessarily be averse to, because I believe that pretty much, like at this point, if we look at Steam Hardware Survey for our, like getting what our SSE platform would be here, it's always moving upwards, you know, and we don't plan on shipping anytime soon. You look at these and it's like, okay, so SSSE E3 and even 4 and 2 are like almost complete coverage. Like no one is doing that. And furthermore, you look down here and you're like, wow, like we could even go up to AVX if we really wanted to, and we probably wouldn't knock out very many machines by doing that. So AVX2, kind of a stretch at this point. So going 8 wide, not necessarily a thing, or using some of that. SSC4A looks like not so good. But in terms of this stuff, we could totally do that, right? So if we wanted to do a shuffle using EPI 8 shuffle, which is a P-shuff-B instruction, right? Yeah. If you want to use the P-shuff-B instruction, then we probably could actually do something here, because what we would do is we would mask so we want everyone to get the value that comes, or we want to put in a known location that we can IMM8 out. We just want to get that value. And so if we just used the mask to produce a shuffle that put the correct value there, I'm trying to think of how you would do that. It's still kind of confusing. Oh, well, okay. Yeah, I'm still not sure, like, exactly how we would do that. You would have to take and do a mask that would tell you, like, you'd have the ones in the correct lanes, but then they're in the wrong set of lanes. Like, you want it to be down in the predictable side. So I guess what you would do is you'd just do a load. I mean, is that really the fastest way to do that? So, I mean, just hear me out. So suppose I wanted to take this min PS here, right? And like, I've got what the minimum value now actually is. At that point, I want to shuffle everything into position so I don't have to do weird extractions. So in other words, what I want to do is then say, all right, instead of get component on any of these things, I want to be able to just get directly the value by using an immediate. So I want to be able to do like this, you know what I mean? Where I just have an immediate, which is always 0, right? So that, you know, so I can basically say like, look, hitbox max, right? I'm going to extract just the 0 value out of it. You know what I mean? So that all of these are just direct and they don't do anything weird, right? And furthermore, I actually don't even need to do that because I can just leave them in here because I'm going to do computations, and now I know they're at the bottom, right? So I don't really have to do those. I could just, at the very end, when I want to actually get one of these out, I can do it. So I can actually just do these directly, knowing that everything is just piling up in the bottom lane, right? So what I was saying is, in order to do that, I could imagine having a pack table where I would basically do like, okay, after you did this, right, you then have a 16 bit mask. So you've got 16 possible values. You can just load up like your shifter, right? Your shuffler. You would say like shuffle table, like your min shuffle table is whatever the mask was. So this thing, right? That you then just apply. So you just do an EPI8 shuffle, right? on each of your actual things. So hitbox min, hitbox max, like all of these just shuffle themselves so that now you know you just have the right thing in that lane. You know what I'm saying to you? You don't even really need to load it this way because you know it's the same value. So you can even, like, this thing is actually like a it's like a propagate, right? Which I don't know that we might just want the load to be one go, so you know we might not do that, but you know it could be a more compact table if you wanted to, because it's the same in each case. So when you grab the shuffle table out like so, I think then you just have everything you wanted, right? So your tmin is now like a shuffle API as well. And it would just look like this. And that would just give you like everything that you actually wanted there, right? And we don't need this mask anymore because you're only using it for that one extraction that you then grab out. Similarly, like this min PS, we don't really care about here, right? So it's really that. So we do this crap in order to get the min value here, which we then comp and output. And at that point, we just say, okay, now everybody shuffles against that shuffle that we loaded out with that mask, right? And then all of our computations can just happen in normal, like, wide space, and everyone's fine with that, right? So this still is just the standard wide version, and we're just not using... Like so it's still doing it's doing it scalar, but we don't need to actually move it to scalar first for any particular reason. You know what I'm saying? So at that point, when we actually do when we actually want to use any of this stuff, we then have to move it out to do this part. And that would be the first time when we actually move it out. And I think that might be where I'll stop today, because I think tomorrow is when I would actually get into implementing this, right? We don't have much time left. I guess we got 15 minutes maybe. So yeah, but like I'll just keep cleaning this up and then I think we'll stop. So all of these would always be 0, right? So these would always be extracts, and we really just have a nomenclature issue here because I want to be able to extract those, and we just don't have a way of talking about those easy, but I think that's basically it. So we would do this. That's not that bad. We'd have a shuffle table. We'd do it. We'd go. I think we can use the table for most of this stuff. So this would all be table driven, basically. And that'd be that. So I think that's good. I don't have a problem with that. And what we could do here is say, like, look, this is also going to be, you know, an elif0 here, and then at the very end we just have another elif. And what we could do is just say, look, we're going to do the transfer PPS bunch of stuff here. Oh, well, you know what? I guess I can't quite do that because we don't like I want to actually test the faster version of that. But I suppose we don't have to do that. Like if we want to, we can just return. Well, no, I really do want to test the faster version of that. So I guess we're not going to do an elif there. I take that back. I guess what we're going to do is more like this. So in here, what we would do, I guess, is just have an if use, or I don't know what this would be, lighting use old KD, or use old, use 4 rays or something like that, right? And in here, then at the end of that, I'm going to put this. And then we're just going to call like grid raycast, and we're going to call grid raycast like 4 times, right? So it's like this. And then we let everything happen. Oops. And then we let everything happen normally, right? So this would just happen by doing a get component to cast the different sets of rays. So this is the ray origin, this is the ray D, but we get a 0 out of it, right? Like so, which is a little unnecessary slow, but it probably wouldn't make it look too bad. So we can still probably do it that way just until we delete whichever one of these paths we've determined is not the right path to continue going down. So here I can just say, look, we're going to cast 4 times. That'll produce the transfer PPS, and then we can still finish up here, right? And then if we decide to vaporize all these passes, we would then just go in here and like clean up the flow so that we're doing the most optimal flow from the top part down to here, right? But I think that's it. And that's so much simpler than the rest of the stuff that we're doing. I would say the only chance that this is wrong is if going 4 wide on these is a bad idea. But even if it was, then doing the load pack swizzle thing ahead of it and feeding it into this thing probably would still work. So I feel like this is probably okay. You know what I mean? So that's what I'm thinking. And it's much simpler, right? So the simpler routine is, the easier it is to optimize. That's just generally the case, right? You don't have to work as hard. So that would be a nice bonus that we would get. There are just a lot less moving parts. You build most of the stuff ahead of time, which is what you want when you're optimizing. Like the more stuff you can do that doesn't have to happen on the fly, the better. So I would say, yeah, that just seems like what we want, right? Like that just seems good to me. So I think that's good. I think, unfortunately, it's going to take us a long time to test this, because in order to make this work, we have to do a bunch of extra stuff, right? We have to add the walk tables. We have to do the work of distributing the cast, like the actual pieces. And then we have to actually run the routine, right, and debug it. So it's going to be a long time to test, unfortunately. That's a bummer. But based on the sketch, I would say I'm relatively happy with that, right? So I'm totally willing to give this a shot. And I think it's, when I was thinking about the KD tree, I'm like, it's not even very good for our fit, because we know all our stuff is axis aligned bounding boxes, and it's like, KD trees are really for narrowing in on arbitrary like distributions of density and stuff like this. And we don't really have that. Like, we have fairly uniform distribution of density, and we know that everything is sort of rectilinear because that's just the way our game works. So it's unclear that we really want a KD tree anyway. So I'm more optimistic about this than going in and working on the KD tree walk. So I think I'm gonna try it. I think this is what we're gonna try. And then if it doesn't perform well, then we'll regress back to the KD tree. We're not going to delete it, but I think that's what we want. Lighting is really simple until you want to make it run in real time. Yeah, I agree. If you just don't care how long it takes, then ray tracing pretty much gives you the answer you want without a whole lot of work. But I think we can probably go to Q&A because I don't think there's anything left to do. We're just going to implement this routine. I'm trying to think of how much time I got 10 minutes left. Well, you know what I could do? I could vaporize this for now, and what we could do here is say, look, we won't do gridcast here yet, so that'll stay out of the way. Turn a null value. And then what we'll do is we'll go do the part where we actually need to fill, excuse me. We can sketch out the part where we actually need to fill in the spatial partition. So in here, where we need to build the actual grid, we can go through this whole thing, right? And so inside the grid build, what do we actually need to do? Well, we're probably going to have to step through the boxes. So we're probably doing something like this, right? And in here, where we step through each of the boxes, what we need to do is find all of the grid squares that that box touches and put them in there. Now, the reason this is kind of a pain in the butt is because we actually don't know ahead of time how many boxes are in each grid square. And so we're going to need like an intermediate way of chaining these things together and then unpacking the chains into compact arrays for raycasting. Because anything we do here, we can be a lot slower here because it only happens once. Anything that happens on the raycast has to happen like hundreds of thousands of times. And so we really don't want to do it in there, right? We want to do anything expensive we want to do here. So it's okay, but we do have to do a little bit of work there, right? And so here we would go through like the node indices, and we would unpack them sequentially. And when we actually figure out where these things go node-wise, again, that's going to be something where we determine the actual node. We don't need this. All we would do here is say, look, I guess these would be v3u's probably. So it'd be something like this. So we take the min and the max of the boxes, and we now know, you know, we would have a v3u for where those were in the voxel for the min and the max. We would step through each one of these, you know, to fill the voxel, right? Just a standard voxel fill, right, of a region. And so we'd say, you know, z is mid node index z, z is less than or equal to mid node index, max node index z. And we'd do this for each dimension. So that would give us everything, that would give us all of the locations touched by, like, that could possibly hit this box. We would then store it so that we'd have to like chain for whatever this location was, right? So if we pass this new voxel location that's somewhere in here, we'd have to chain this box onto whatever that was, right? So the the solution, we'd want to access that node index. We'd want to chain it on here. And then when we're done with that, we would loop over all of the nodes, right? Which would be however many was the x times the y times the z total. And for each one of those, we would need to sort of undo that chain, right? Now, we know ahead of time how many of these we actually need, and we could pull it out of temp memory, potentially. I mean, I don't know if we want to do that or not. But we know, like, the total leaf count at this point, and we can sum it because we know here's how many there are. So when we go to the nodes, then what we're really doing is we're just saying, here's our, leaf index currently, which is going to start at 0. We go through each of these nodes and we loop over however many they have. So we're going to need like a thing for the node where we would get that out. And that'd be the same as this. So we would get one of these out. We would do the chaining here, however we want to do that. And then in here we would say, all right, for each of these, we need to loop over all of the lighting boxes that we chained onto that. And this could be a linked list of some kind, right? It wouldn't probably look like this because we'd probably chain off a U16 since we know that they are that way. So we'd probably do something more like, look, off of the uint16, off of the node, we grab a U16 that's like the first in chain, and then we say like chain is not equal to like chain end or something, this kind of thing. And honestly, this probably has to be this way because we're going to go look this up, right? We would then say, all right, which box is this thing? And once we get that, we can do like next in chain as a thing that we would chain off the boxes. So for each of those, then this is where we actually do the work. So once we know that this thing is going to be packed, we would pack it here. And so when we do the packing, we're doing packing into this thing. And so we would need a pointer basically that tells us where we're packing, how we're packing, right? And we need this to be so actually we don't pollute the cache, we just waste instructions because this doesn't have to be aligned. So actually we just pack this linearly, right? We can just pack this linearly, and all we have to do is store how many you need to load, but we don't actually need it to line up. Like you can just load extra boxes off the end of this thing, and we just have to make sure we pad it. So we need to do like a while leaf index mod 4 at the end here and write garbage in there. You know what I mean? But other than that, so these would just, I'm not sure what the best way is to produce something that cannot hit. It may be that this is bad because if you pass directly through the origin, it would technically be considered a hit. You know what I mean? So that seems bad. It's never going to happen, like, in any way that we would care about, but it does seem like maybe you would want to avoid it. So what you could do here too is pad it out with something that you just can't really hit. So like, something that's like off in the stratosphere might be the right way to do it, right? So it's like an inverted box that's off in the stratosphere and, you'd never hit it. Or I guess you could even do it this way. that might be the easier way to make sure that you never hit that thing. I'm not sure. Like, we should just put it to do in here. That's like, what's the best can't hit me box for our actual box collision test? So if we do it that way, this would be everything that we need to, and we just need now a way to do the chaining sensibly, right? But I think that's it. So I'll end it there, but we now have everything sketched out, so now we just gotta actually do the implementation. There is one thing I didn't do, which was the walk stuff, and the walk stuff is literally just doing a ray walk. Like, we can even do it just offline. We don't have to get fancy and figure out what it would be. For every one of the rays we store in our ray table, we just store like which table index it uses for its walk. And a lot of those would probably be the same. I mean, maybe they won't be, but if there's any duplicates, we just remove them. And then that way we just load directly out of the table what we're walking, and that's it. So I think that's good. We can go ahead and go to Q&A now. Could you use a couple of M's, horizontal subs, to do your horizontal compare? Possibly yes. And in fact, if we do decide that we can use SSE4, we probably have a couple different things we could look at. Which, like I said, using the Steam hardware survey, it looks like SSE4 is probably pretty safe to use. So we have a couple things, horizontal things that we could use, right? So if you imagine that is our actual target, then we actually have a bunch of stuff here. I mean, so if we want to just use SSE 4.1, that is the entire instruction. Right? I mean, that's the thing. So I think, like, we could just say, look, man, let's just use it. And we can always have a slower path later if we decide we really need it. But that, I mean, that's the instruction. It does the whole thing. So, you know, I can just say, like, literally do minpos EPU 16 and get what I need, right? Because if it, like, SSE, AVX 512, eventually you get far enough up there, they've got the actual correct instructions that you wanted them to have in the first place. It's just a matter of how far up you're willing to go along there, if that makes sense. So if we want to, we can say, you know, am I not? There we go. So I'm not sure which, if I have to prep it for this though, because it's not a PS, right? So I don't know if there's a minpos version of that. It looks like the only thing they've got is the 16-bit one. So I'd have to kind of like put it into that format first. So I take it back. That may not be quite what I want, because you want the minpos PS, right? Which apparently you can't get, because they only have that for just that one instruction. which is hilarious. But so maybe not. We could make that work. We can pretty trivially turn our RT values into 16-bit values. That's not that hard. So we could just do that instead. We'd take the T min, the T max, and we'd bracket it. So we'd say, look, we know we don't care any, like this thing is only so long. So we'd say map into that range. So first multiply the inverse, convert to 16-bit, and do the min pos EPU 16. Right. So it would just be this. So we just say multiply this first by what we know the maximum hit value is, and we would change this to be whatever that maximum hit value was. And then we would do a min pos EPU 16. That would get us back our min test. We would then use that to shuffle everything, right? So instead of this, we would then have like shuffler equals some shuffle of the min test, which would just move the correct values around that we need it to use for this. You know what I mean? So we could do that too. I'm just not sure, like, this part of the code is not the part that runs the most often. So the thing that runs the most often is this, right? So this we need to make sure is very, very fast. This cannot be slow. This part here, is it 2 instructions? Is it 10? It will make a difference, but it's unclear how much of a difference. So it's unclear that you want to, if this part of the routine could be made twice as fast by switching to SSE4, you'd definitely do it. If this part of the routine can be made twice as fast by switching to SSE4, it's unclear that you care. You know what I'm saying? You might just want to stick with the simpler case. When it comes to game dev, engine dev, what do you believe is the hardest part to implement? Lighting, editors, etc. I would say probably like infrastructure is the hardest thing. So like the circle that you draw, that is, what is the storage format for both editing and runtime? How does that get processed, edited, saved, shared, optimized? The infrastructure part is by far the hardest because it has all of the worst things. It has to be edited, so it has to be flexible. It has to be looked at broadly because optimization often pulls from multiple things to produce the output assets you actually need. It needs to have fast turnaround time so that artists can see their work in the game. It's massive because it includes the sources. It's way larger than the game by many powers, like 100 times larger than the game. If the game is 23 gigabytes, then the source, assets for that game are probably like, 23 terabytes or something, right? So it's like 1,000 times bigger. How do you switch that fast between navigating into code and typing? Am I fast? I mean, this is me doing the arrow keys, and then I go into typing and I just start typing. I mean, I don't know. I don't know. It's not very far. Uh-oh, are we getting raided? We're done. How can we get raided by John? I was gonna go raid John. Though. What are you doing? When am I gonna have lunch? Unacceptable. Unacceptable. This is completely unacceptable. All right, well, hold on 1 second. Let me get a drink or something. Because, yeah, you know what? Hold on 1 second. Like, let's end it here, and but I'll keep the stream going and I'll think about it. I'll be right back. But I'm gonna get at least a drink then.